science. We're going to go ahead and get started in 3 minutes. Alright, so as we're waiting for the countdown to wind down, go ahead and take a look at the notes that you had from yesterday, if you took any. Okay, we're going to continue to work on the building electromagnet that we did yesterday. Class on today's meet. Are they with us yet? Okay, so at each table, here's what we're going to do. We're going to break up science into 3 periods. We're going to take the periods from 9:15 to 9:30, 9:30 to 9:45, 9:45 to 10 o'clock. So there are 3 periods. Okay. Raise your hand if you're an officer. 1, 2. So Jackson, you're in charge at that table. You're in charge here. Callie, you're in charge there, and Leah, you're in charge there. Which means from 9:15 to 9:30, you find someone at your table that's going to be in charge of today's meet. They need to make sure that they're checking it regularly. If your table wants to post something, they can post it on there. If someone asks a question, they should read it to the class. They should read it to your table and see if your table can provide an answer. Okay? At 9:30, you switch it out. Pick someone else. And then at 9:45, pick someone else. So there should always be someone at the table whose primary job is going to be the today's meet jockey, I guess we could say. Okay, you're on the computer, you're constantly checking, you're constantly making sure that you're aware of what's going on. Make sense? Okay, so right now, officers figure out who that person is going to be to start off. Here's what I'm going to tell you. It should be someone who's on task. If someone is not writing in their notebook, not participating in science, it should not be that person. Okay, so if someone is on task and they're working and they're being a part of the group and doing all that stuff, then allow them to be. Okay, so if you want to be the person that's on today's meet, that's the way it's going to work. Okay, so find someone, and we'll go ahead and get started. All right, so we're going to go ahead and get started with the second part of building electromagnets. Now, just to review, yesterday, one of the things that we took a look at was we went to our notebook, and we asked this question: how can you turn a steel rivet into a magnet that turns on and off? Now, there is one way to do this, and we're trying to figure out what that way is. And so just to kind of come back and review very quickly, we created an experiment yesterday where we took some wire and we took some components of a circuit. We built a circuit, and then we put a compass next to that circuit. And when we turned on the circuit, we discovered that the needle of the compass would move, which is indicative of what? Why would the needle move? There's got to be magnetism there. The magnetic field is what causes the needle on the compass to move. So we discovered that when electricity travels through a circuit, there is magnetism. Now, was there a lot of magnetism? Not a lot, because the needle didn't move a whole lot. We've discovered that the stronger the field, the more the magnet moves. Okay, let me give you an example. So here I've got one of these donut-shaped magnets that we've used, and you notice that if I put it around here and I move it around, the needle does move. Okay? Okay. It moves, and I'm not very close to the magnet, but it moves. Okay, you can see that. Okay, now I've got an even stronger magnet. This is a rare earth magnet. This is a lot stronger, and you're going to notice when I bring this, okay, look how far I am, and the needle's already moving. If I bring it in closer, you're going to see that the needle really starts to go crazy. Okay, so why does the needle react stronger to this magnet?
Because it's really strong.
It's got a stronger magnetic field. Okay, so the strength of the magnetic field makes a difference. So how strong is the magnetic field in a wire with the circuit? Was it really strong?
No.
Not really. Which means that in order for me to take a rivet and cause this to turn into a magnet, I would have to have a lot of magnetic field around it, right? I could take a simple magnet like this, and then I could test it to see if this is magnetized by dropping some washers and saying, all right, let's see if this has become a magnet. And you'd say, yeah, it has become a magnet. Now, how many washers can it pick up?
3.
Okay, right there, I picked up 3. Okay, and if I really rub it in, I might even be able to pick up a few more. Okay, but you see, it's based on the strength of the magnetism. Now, if I were to take my rare earth magnet and attach it there, this magnetic field is a lot stronger. How many of you think that this will create a stronger magnet in the rivet? Okay, so let's take a look if it's stronger. So what I'm going to do is get these washers here, and let's see if you are correct in that it creates a stronger magnet. Okay, it absolutely creates a stronger magnet, as you can see. Okay, so the stronger the magnetic field, the stronger the rivet will become. Okay, so if I have magnetism in this wire, but there's not a whole lot of it, how could I get more of that magnetism around my rivet? It's got to be close to the rivet. Remember, we also learned that the magnetic field is strongest next to the magnet, or touching the magnet. So if there's magnetism on this wire, then that means that where would the magnetic field be strongest? Right next to the wire or far away from the wire? Right next to the wire. So if I have a really long wire, how could I get the magnetism from that wire onto the rivet and get as much of it as possible? Serenity.
You have to wrap the yellow wire around the rivet a bunch of times.
We'd want to wrap the wire around the rivet. Okay. Now, the other thing that's important to remember is that you don't have a circuit if both ends aren't plugged in. Okay. Yesterday, and we talked about this yesterday. Yesterday, as I walked around, I saw many of you doing something, and it reminded me of a saying that we have in our classroom. Okay? A lot of you said, oh, okay, so I'm just going to take this and I'm going to wrap it around. So what you did was you took the wire, okay, like I have here, and you proceeded to then take the wire and just start wrapping it around the rivet like this. Okay? And so I'm wrapping. It's going to take a little while because it's a long wire. Okay? So you did this, and then you had basically this. You had the wire wrapped around the rivet, and you had one end of the wire left over, and you took this end and you plugged it into the battery, and then you're trying to see if it works. Okay? And so what that tells me is, well, number one, is this a circuit?
No.
Why is this not a circuit?
It's not resisting the flow.
Okay?
Electricity isn't coming out or going back into the cell
How do you know that?
because it's not turning into a magnet.
Okay? Well, maybe you've done it wrong. How do I know that this isn't a circuit?
Because there isn't one path. It's just like one wire plugged.
There's no path. If this wire is hooked up to the battery, where's the path that takes it back to the cell? There is no path, is there? Okay? So because there's no path, there's no circuit. There's no electricity flowing through this wire. And what that tells me is that, sure, you learned what a circuit is. You know that a circuit has to start at the cell and it has to end at the cell. But yet, you do this. So what does that tell me? That you have learned something, but you are not using it. Those who learn but do not think are doomed. Right? There are some kids who don't quite understand circuits, but they understand both ends have to be plugged in. And so they will plug both ends in, but they're still trying to learn more stuff to figure out how to make this work. Some of you have learned what a circuit is, but you don't use it. And then you plug this in, and then you're shocked that it doesn't work. Okay? You have to use what you've learned. And here's what I'm going to tell you. Everything that you've learned about circuits right now, you're starting to apply. Okay? Which means what you learned about magnetism yesterday is going to be used to build this. What you learned about circuits weeks ago, you're going to use to build this. Okay? So, in other words, you might have to go through your notebook and start going to old lessons to get ideas on how to work on this. Okay? So, science is not something where you're going to have a lesson that you did 3 weeks ago and you no longer use it. Okay? You absolutely use it. If you're struggling with this idea, you might want to go back to yesterday's lesson and say, what did I learn yesterday? Now, how can I use that to build this? What did I learn 2 days ago? How can I use that to build this? Okay? So, the idea remains the same. Okay, I'm going to give you today, since you got an opportunity to work on this yesterday, I'm going to give you about 5 to 10 minutes today to work on actually putting this together. Now, here's the other thing. Once you build your circuits, do not, I repeat, and this goes for everyone in my class, everyone in Miss Richards' class, and Miss Taylor's class, do not turn on your switches until you are ready to test your circuit. Okay? Because if you actually have a circuit where the wires are hooked up to the circuit and you turn on the switch, that electricity is going from the negative to the positive, and what's stopping it?
Nothing.
There's nothing. Is there any resistance to slow down the electricity?
No.
There's nothing. The resistance would normally be a light bulb, a motor, any device that's in between. If you just put a wire from the negative to the positive with a switch in between, does the switch provide any resistance?
No.
No. So if there's no resistance, nothing to slow it down, how fast can the electricity go from the negative to the positive? How fast?
Fast.
Extremely fast. There's nothing to slow it down. Therefore, that means you can drain your battery in a matter of minutes, and you will have a dead battery within 1 to 2 minutes if you're not paying attention to what you're doing. So at your tables, I'm going to have one person in the science group. Your job is simple. Your job is to make sure that the circuit is never on until you're ready to test it. Figure out who that person is going to be, and when I walk around and I ask, who is your circuit monitor? You should be able to tell me who it is, and that person should be making sure that the circuit is not turned on until we're ready to take the rivet, put it on washers, and then turn it on to see if it picks anything up. If it doesn't pick anything up, I turn it off again, and I try something new, and then I say, all right, we're ready. You stick it in the washers, turn it on, see if it picks anything up. If it doesn't, turn it off again. Okay? So you're only turning it on for like 2 to 3 seconds to see if the rivet picks anything up. Make sense? Does that make sense?
Yeah.
Yes? Clear? Okay. All right. So, getter ones, grab your materials. Let's start building. You have 10 minutes.
You give me circuit manager.
No.
So Jade, who's in charge of today's meet right now? Who's in charge of today's meet here today? Till 9:30. Sam? Who's in charge of today's meet at this stage?
I got rid of
Look, how about here? Who's in charge of today's meet? Okay. Right. So at 9:30, switch.
Okay, I have an idea. Yeah. I have an idea, guys. I know someone's on science.
What were you supposed to do? There should be switches, guys. There's some switches here. There should be yellow wires, guys. Hey, ladies and gentlemen, no one should be taking more than the yellow wires that you need. Where are all the science materials? Is there anyone that does not have yellow wires? Take this one, Logan. So build a circuit. I'm going to come around and give you some washers. You're going to need a circuit base. Make sure you have a circuit base.
And also the negative side is supposed to be attached to the
Okay, so how are you going to hook up the other end of that wire?
I don't know. Okay, it goes like this, and then a red wire connects to this.
And where does that red wire go? So how is there electricity going through that yellow wire?
It's not right now. Sorry.
But even once you do this, and I want you to think, you're not thinking. Grab a wire. Just grab another wire. So if I put a wire here, and I do this,
Oh, yeah,
okay? Need you to think. Once I do this, once I turn this on, where does the electricity go? How is it going to go through there? Okay. How would the electricity go through there? It won't, because there's no way for it to get back. It has to get back to the cell. If it can't get back to the cell, it's never going to go through here. To the end of the, how are you going to get to the end of this wire? It's all wrapped up down there. So if you take the red wire and wrap it around this, it's still not going to work. Because this wire and the red wire aren't connected. Right? I can't put one wire here, and still, okay, now it's going to work. So is the electricity magically going to jump from this wire to there to here? How is it going to go through the metal? Explain that to me. Okay, so wrapping it like this. So how are you going to make sure that doesn't touch it? Why not just connect this other end to your circuit? Why not just put this end and connect it? So you have a path for the electricity would go through this.
Well, if you don't,
Right? Okay.
just at least let me try.
No, not working. Okay, so something's off. Something's not working. Okay, so one thing I can do, because some people have abused the cell, is make sure that the cell works. Your cell definitely works. Okay, so you got electricity flowing, it's just not working. So you might want to maybe come up with a different way.
Turn it on.
Okay, but before we do it,
I just hit it right there. So how? It wasn't powerful enough.
whenever I tell you, you say no, and then I'm just
Checking.
Should work. Oh, it's on.
So you have something that works. Try it again. How do you turn it off? So try it. Pick something else. Turn it off.
Oh, that's probably how they work. That's actually the same.
Okay, we're down to less than a minute and a half to build. Have anything yet? Yeah, you have a whole bunch of extra wires. I have that much extra wires. I would wrap as much of it as much of that magnetic field as
Wrap the wire around
It's not a circuit because this
Oh, that was when Mr. Pillow asked.
we're never gonna do it.
I would like to do it.
You got choose a person that's
I'm not concerned, but you get here and then so what's not hold on, I think that we will get this on
Alright, ladies and gentlemen, let's stop for a second. Hands on your heads. 5, 4, 3, 2, and 1. So, we actually have a group that has a built working magnet that they can turn on and off. Has anyone else successfully been able to get it? You guys got yours working? Okay, anybody else have theirs working right now? Okay. So, before we actually get into the details of how this is going to be set up, what strategy do you use, Kaylee?
Since the yellow wire is so long, we wrapped up a lot of it and then like just a little bit on each side of the ends so that we can hook it up to the cell and switch.
So you use most of the yellow wire since it's so long, okay? How about this group here? What strategy did you guys use?
We did the same thing. We just kept wrapping it up on one side and then and then we moved on.
Now, did you wrap it all over the rivet or just like on one part of the rivet?
We wrapped it on both. I mean, it would have been better if we did on one because it would have been more energy, but that's
So you wrapped it all over the rivet?
yeah.
And how many did you guys pick up?
Like
3? How many did you guys pick up?
4. About the same. About like 2 or 3.
Okay.
4, yeah.
All right. So did you guys wrap it all over the rivet or just on one part of it?
All over it. Like one whole end.
Did you wrap it? In other words, did you wrap it all over the rivet or just on one end?
Just on one end.
Okay. So if you take a look at your rivet, and I'll hold the rivet up. So some of the teams that have done this, they didn't wrap the wire along the entire rivet. They just picked an end, either this end or this end, and wrapped the wire there. So that might be an idea that you can try. Okay. In the meantime, let's take about 5 more minutes to give everyone else a chance to try to build this. For those of you that already have it built, I want you to test what you came up with, see how many it can pick up, and then kind of change your design and see if you can make it better. How would you know it's better? Kaylee, how would you know it's better? Picks up more than what you did the first time. So for those of you that haven't done it, try to build it. For those of you that have built it, change your design and see if you can get it to pick up more. Okay? All right, 5 minutes. So test it and see how many you can pick up right now. You got to test it first. Pick them up. Bring it on. Turn it off. And you picked up what? 4. So now you want to see if you can build a better version that picks up more than 4. How many do you guys do? So now, now, let me ask you a question. Remember, your magnetic field is stronger.
Okay, let's try it on Sam's idea. Let's do that. Let's pick this. Yeah, that one. This is just for
You're probably going to want it really tight, like as close to the river as possible, which means that you might, this doesn't make it.
keeping with the same idea.
You've got all of these wires here. So what you might want to do is figure out how to get this to work. Every single wrap is as close as possible. Make sense? So you might want to take this out. How can I grab this? How can I grab it as close to the river as possible?
Just do the way I did it.
So you're able to pick up 4. So can you tweak it and adjust it to try to make it pick up more? How about here? Okay, do you have a circuit there? Here, you guys have a circuit there? If you have it, going back to the south.
The switch is off. You don't have to.
Otherwise, you're stuck right here. How are you going to maybe like this? I have a little bit of this.
first, then we could do your idea. But now and then they came up with a complete new idea, and they keep coming up with new ideas, and I don't get to explain mine.
Okay. So did they finish the idea they had?
Yeah, but now they're doing the new one.
Okay. Mr. Braden, science materials are off limits for you. Okay, group 1. Until you can prove someone's idea wrong, you don't just throw it out. Okay, so you've got to give her a chance to give her idea. If it doesn't work, it doesn't work. Okay, but you can't just negate it and not use it. All right, ladies and gentlemen, time's up. All right, so let's stop. How many of you were now successfully able to build an electromagnet? Okay, good. Was there any groups that weren't able to build it? Okay. All right. So what happened at this group? Why were we not able to build it?
Lack of teamwork.
Okay. Lack of teamwork? Is that an issue if you have lack of teamwork? Does it make it harder to work?
Yes.
It does. Okay. So, let's see. My team 6 over here. How did you guys design yours?
Basically, we just kept on wrapping the wire at one part. Since we just tried putting it in the middle and then tried to pick up some washers, but then it didn't work twice. So we got kind of frustrated. But then Sam had an idea like, let's wrap it around on top, and then on the top part and just that one part, and we were able to pick up like 2 washers with it.
Okay. So should we all still be building circuits right now?
No.
Xander? Should we still be playing with science materials?
Yeah, just
Doesn't matter. Okay. We should not be playing with science materials. Sam, should you be playing with the wire right now? No. Okay. 2 wrongs don't make a right. If someone grabbed it and you're like, well, they grabbed it, so I grabbed it. Well, then you're both wrong. Okay? Once the discussions start, and I say stop, we stop. Otherwise, you're not listening. You can think you're listening, but you're not. Okay? So the idea is to wrap the wire around the rivet as much as possible. Turn on your circuits, and then make sure that you test it by trying to pick up the little washers. Okay? All right, so as we continue to build these circuits, what we need to do is we need to create a standard. In other words, we need to make sure that everyone's doing it exactly the same way so that it makes sense when we make comparisons. When we start to compare one person's electromagnet to someone else's electromagnet, we can't compare them if they're built differently, can we? What if someone wraps it 10 times and another team wraps it around 50 times? Okay? Could that make a difference? That could make a difference. Okay, but before we go, let's come to our notebook here. So in your notebook, we're going to add a few things. Okay, so what you built just now has a name. And I'm going to put here that you're building, and I'm going to change the color here. You're building an electromagnet. Why do you think it's called electromagnet? Vincent?
Because it's a magnet. You use electricity to turn it on and off.
Okay.
And on and off.
It is a magnet that uses electricity, okay, to be able to be turned on and off. So it is called an electromagnet. Okay? An electromagnet is made using a wire that has electricity flowing through it to produce something called, so I'm going to write this here, the wire with electricity makes electromagnetism. Now, we know what magnetism is, right? Magnetism is what a magnet has. Magnetism is the magnetic field that is around a regular magnet. Now, when electricity is flowing through a wire, it creates something called electromagnetism, which is still magnetism, but it's a special kind of magnetism. What's special about electromagnetism that's different from a regular magnet? Leah? No. What's special about electromagnetism versus regular magnetism?
It's not always a magnet.
It's not always a magnet now? What is magnetism? Vincent?
Magnetism is it's like a little force field that can pick up metals and stuff.
Okay. Magnetism is a field that a magnet has, right? What is electromagnetism?
It's a field.
It's a field,
But it's made out of electricity.
okay, that is created using
Electricity.
electricity. Okay? So electromagnetism is not an electromagnet. Does that make sense?
Yeah.
There's a difference between an electromagnet and electromagnetism. Okay, magnetism is not this. Is this magnetism?
That's a magnet.
This is a magnet. A magnet has magnetism, but magnetism is not this, right? An electromagnet has magnetism in it, but electromagnetism is not a magnet. Okay, so it's important for you to make that distinction. Get that right now, click it in your head, that when electricity goes through a wire, it makes electromagnetism, which means there is magnetism that is being made through the flow of electricity through the wire. Okay, the same way that a regular magnet has regular magnetism, a wire with electricity flowing through it has electromagnetism. So, they do the same thing, but there's a difference. Okay? This is making magnetism, a magnet makes magnetism based on the alignment of the atoms. A wire makes electromagnetism based on the flow of electrons as they move through the wire. It creates electromagnetism. So it's important to notate that. Okay, electromagnetism, and I'm going to put here, this is not a magnet. Electromagnetism is what the wire makes when electricity flows through it. So I would say when this, that was a bad this. So when this electromagnetism comes in contact with the steel rivet, it creates what? What does it create when this electromagnetism in the wire comes in contact with the steel rivet? What does it make? What did it make when you built the circuit, wrapped the thing around and turned it on? And all of a sudden, as soon as you turn it on, there's electromagnetism around that wire. And what causes to the rivet? What happens to the rivet? Okay, it turns into a magnet. What kind of magnet? Okay, that's the name of it, but what kind of magnet is it? Leah? It's a temporary magnet, but what kind of magnet?
Induced.
An induced magnet. What does that mean?
It's magnet.
An induced magnet is a magnet that was created how?
With another magnet.
With the magnetism of another object, right? If I take a steel rivet and I bring it in the magnetic field of another object, it will become an induced magnet. So if I take this rivet and wrap it around with the wire and turn on the electricity, that electromagnetism is going to affect the rivet and turn it into an induced magnet. It's not a magnet on its own. It has to be induced to become a magnet. Okay? Does that make sense? All right. So there are a couple of other things that I'm going to tell you that are important, because electromagnets, believe it or not, are a big deal. They are everywhere. We use them for tons and tons of stuff. And we'll talk about what kinds of electromagnets we have. Okay, so you need to know some vocabulary. The steel rivet is called the core. So in every electromagnet, whatever is in the middle that has the wire wrapped around it is going to be called the core. So we're making one with the steel rivet. Can you make it with any? Could you make an electromagnet with a nail?
Yeah.
Yeah. Could you make it with a paper clip?
Yeah.
You could make it with anything that's made out of
Steel.
or that has iron in it. Anything that has iron in it. Okay? And you're going to wrap wire around it. Whatever is in the middle is called the core. So from now on, you're not going to say, Mr. Perla, I can't wrap this wire around the rivet. You're going to say, I cannot wrap this wire around the core. Okay, we are no longer going to call it a rivet. It is a core. Okay? Now, let's go back to the next part. The wire around the what?
Core.
The wire around the core is the coil. Two new words that we're going to add here. Coil and core. So as you're building electromagnet, I might come up to you and say, how tight is your coil? If you don't understand what that is, you're going to be totally lost. I might tell you, check the tightness of the coil around the core. You better know what that means, because I'm no longer going to call it a wire and I'm no longer going to call it a rivet. Okay, so as of right now, we need to make sure that we get used to the idea of changing the way we speak, because we are learning vocabulary. We're learning how to speak science. Okay? So, from now on, what we want to do now is we want to go through, draw our electromagnet, and label all the different parts. So, how do I do this? Okay, so I'm going to draw a diagram here. I want to draw a diagram of what this electromagnet actually looks like. Okay, so what was part of my electromagnet? Well, I had several things. Okay, and we'll take a look at the items right now. So let me clear my ink here. And if I go to my desk cam, I had a what? I had a core. Good. I thought you were going to say you have a rivet. I had a core. What else did I have? I had a coil around the core. I had a switch. And I had a power source. Okay? So these are the materials that I had. So what we want to do right now is we want to draw this. So how am I going to draw this? So let's come back to our notebook. And we want to focus primarily on the electromagnet. Okay? So you may want to look at your core and draw your core. You'd say, okay, well, my core looks something like this. Okay? So my core looks something like this. And then I had, what did I have? I had wire that came around and was just
No, it's not wire.
Okay? Is it wire?
No.
It is wire.
Yeah.
When does it stop being wire?
When you
Once it's wrapped. Okay? So when I say I had wire that came and was wrapped around the core, that is correct. But once it's wrapped around the core, I no longer call it wire. Now I call it a coil. It is now a coil. Okay? So don't come up to and say, Mr. Perla, can I borrow some red coil? No, the wire is still wire. Once it gets wrapped around an electromagnet, that now is no longer called wire. It is now called a coil around the core. Okay? So we're not changing the name of wire and calling that a coil. Okay? The whole wrapping around the core is called a coil. So as I label this is still wired, right? Okay? This section here is called a coil. Do you see the difference?
Yeah.
Do you see the difference, Les? There's wire wrapped around the core. Where it's wrapped around the core, that's the coil. This is called the core. Anything else I need to label? Or was that it?
That's it. What about the zip around
You forgot the switch.
Okay, we already know what the switch is, right? We know what the switch is, we know what the power source is, we know what the wires are. Okay, but here we need to label and diagram the new components that we're learning about today.
What about the
Okay.
black stuff?
Now, what we need to do is we need to come up with some standards on how we're going to build these. So, we're going to stop in just a minute. The last thing we're going to do right now is we're going to come up with some standards on how we're going to build these electromagnets. And the reason we want to do a standard, okay, is because we want to make sure that we do it the same for every group. Now, before we do, I'm going to put something up here for those of you that are kind of curious. What does the electromagnetic field look like? We know what it looks like in a magnet, right? It has a... what does it look like in a magnet? If I drew a magnet like this, what does the magnetic field look like for that?
You have
Okay, goes from right? The magnetic field looks like this because it goes north and south, right? What would it look like what does electromagnetism look like? Because there is no magnet. A wire is not a magnet, is it? So what would that look like? Pretty interesting. Okay? So if I had a wire that was flowing like this, and let's say this is the negative end and this is the positive end, because we have a battery, right? We have a cell. And one side of the cell is hooked up to the negative end, the other side is hooked up to the positive end. So what does the magnetism look like in that wire? We know it has to have it, right? Which means it has to have a magnetic field. What does the magnetic field look like? Any ideas? Alright. So I'll let you know. It looks like this. It goes around the wire. And it goes all the way down the wire. And what I want you to realize, it's little arrows. So the magnetic field is actually going around the wire.
So it's not going directly through.
So as the wire is traveling, the electromagnet magnetic field is actually going around the wire. So it's not like a regular magnet where it leaves the north or south and goes towards the other side, because a wire doesn't have another side. It's just round. And so the electromagnetism actually circles around it like this. And so it's very small and it's very close to the wire, which would explain why you have to do what with the electromagnet to work. You've got to wrap it pretty tight around the core to get that electromagnetism to work. Okay? So this is what it looks like. And we've labeled it. And now we need to come up with a standard. So this is where we're going to end. So we're going to call this our standard. So make sure you include this in your notebook, because we're going to build electromagnets using this standard every time. So our standards for electromagnets. Okay. So let's say so that everyone's on the same page. We're going to say that we're always going to use 40 wraps, which means you're going to go around the core 40 times with the yellow wire. 1, 2, 3, 4. So you're going to wrap it around 40 times. That way everyone has exactly 40 wraps. Okay, the next thing that we want to do, we want to wrap between the head and rubber washer of core. Okay, so I'm going to show you what that means on the dot cam here. So when I take a look at the rivet, the head of the rivet is this part, the top. The first rubber washer is here, down at the bottom. So when we say we always want to wrap between the head and the first rubber washer, that's what we're talking about. From the head to the first rubber washer, and the wire is all wrapped up in that section. Okay, so that's going to make it easier for us to do it that way. So you're always going to wrap between the head and the first rubber washer. Okay, the next thing I want to do is to make sure that you wrap the wire in the same direction. Okay, so don't start wrapping one way and then halfway through you decide you're now going to wrap it the other way. Because what's really interesting, think about this. If the magnetic field goes around the wire, what would happen if I wrapped it one way and then wrapped it the opposite way?
It would unravel.
Well, not if I did it tight. If I start wrapping it one way and the magnetic field is going around, if I started wrapping it the other way, wouldn't the magnetic field now be going backwards? Opposite. So what do you think those two magnetic fields would do to each other?
Crash.
They would crash into each other and they would
Disintegrate.
cancel each other out. Exactly. The magnetic field would actually disappear because one magnetic field is pushing on the other, and they kind of make each other disappear. And now, even though you turn it on, there is no magnetic field because they're canceling each other out. This is why you want to wrap in the same direction. Okay? And then finally, the last thing that we want to talk about. Okay? Pick up washers with the head of the rivet, or of the core. And the head is which part? The little round part, right? Where you're gonna pick up the washers with the head of the core, and this is only if it's possible for every class. Woo! We want to use 2 cells hooked up. How do I get the most force in a series? 2 cells in series. If you don't have enough cells to do 2 cells in series, then you can do 1. But if you're going to use 2, you always want them in series to create the most, the highest voltage that you possibly can. Okay? And we want, so 2 wires in series with the wires as close as possible to the power source. Oh. To the terminals. Okay, which means I don't want to hook up my two cells together with a huge, giant, long wire, because what happens as the electricity starts to go through that wire? Is there resistance in the wire?
No.
Does the wire slow it down at all? Is there resistance in our hallway?
No.
No? Does our hallway have, if I ask you to run down the hallway, does the hallway provide resistance?
Yes.
Yeah. Some, not a whole lot. But compare the hallway to being outside. What provides more resistance, the hallway or outside? The hallway. Okay, so even though the wire allows electricity to flow pretty easily, is there resistance in it? Yeah. There is some resistance. Not a whole lot, but there is. Now, if I make the wire longer and longer and longer, am I increasing the resistance?
Yeah.
Yes. So if I want the electricity to flow as much as possible, what do I want to do? Make the resistance as small as possible by doing what? Shortening the wire. So therefore, when I hook up two cells in series, don't hook them up with a big giant long wire. Hook them up with short wires. And that's why I say with the wires as close as possible to the terminals. That's going to limit the resistance between those two cells and give you the most power that you can possibly get out of those two cells. Does that make sense? Okay, are we clear on what the expectations are for our circuits moving forward? Alright, so that was the plan for today, for you to actually build these and understand how to build them, put some standards together, and later on this afternoon, we're going to investigate different ways to try to make these electromagnets even stronger. Okay, so right now we just learned how to build them. Now we're going to say, now that I can build it, let me tweak it, let me find better ways to make it stronger, and see if we can come up with something as a class that's going to give us the strongest electromagnet possible in the class. All right, so with that, we're going to go ahead and log out. So thanks for joining us, Miss Richards' class, Miss Taylor's class, and we will touch base this afternoon at 2:45. Take care.
Bye.